All right, and we're back. This is another tutorial on solving first order ordinary differential equations using numerical solvers in Python for intermediate mechanics. That's physics 2500, and I am Dr. Hammond. We're going to continue on just a little bit talking about Euler integration before we move on to midpoint. I realized that I have this example here that shows that you can calculate the number of steps and how long it takes. And so this is on my computer, that as we increase the number of steps or decrease the time steps, that we can actually measure how long this takes and calculate what the error is. And so for something that, for this ball that travels, 100 meters or so over 5 seconds, you can see that if we only have 100 time steps, that this error, so the exact solution is something like -15, whereas what we calculate from our numerical solver from Euler integration is about -14 meters. And if you take the difference between the two, it's 1.2 meters or so. But you can see that how long this takes is almost instantaneous. It really takes no calculating time at all. It's so fast, in fact, that this is some feature of this timing thing that it records it as 0 milliseconds. But if you increase this to 10,000 steps, then it takes 156 milliseconds, but still a fraction of a second, so you don't really know you don't notice how long this takes. But this error is on the order of 1.2 centimeters, and so that error is quite small. But we can increase the number of steps by an order of magnitude, and you can see that the error decreases by an order of magnitude. And so that's what I'm saying when the error goes as the delta t, then that means that the delta t here, of course, is decreasing by an order of magnitude as we increase our steps by an order of magnitude. And so the error here decreases by an order of magnitude. But you can see that after about 1 million steps or so, that this starts to increase the calculation time as well by an order of magnitude. So at 100,000 steps, it takes 0.2 seconds. At 1 million steps, it takes about 2 seconds. And at 10 million steps, it takes about 20 seconds. The error is, of course, very small, but the number of these steps is huge. It says it takes about 20 seconds, but then actually trying to plot this 10 million data points on Python actually kind of crashed my computer, so I called it computer borked. So I will let you try and do that at your own peril to see how long it takes for you to run these. But I would probably suggest doing under fewer than 1 million steps. But you can see that the error almost exactly matches the exact solution. So that's why Euler integration requires so many steps. So as I said, though, Euler integration is not actually a very good integration routine. So we can do the next easiest one is called the midpoint method. And so how the Euler method predicts this next point here is that it takes the slope at this point and then predicts this. But you can see that if this thing is rapidly changing, that it's going to greatly miss what the next step is. So what the midpoint method does is it also takes a half step and then calculates the slope there to predict where this is going to be. So you can see that this is going to greatly improve what this answer is. So the midpoint derivative would be that at time plus 1/2 of this time step is going to be equal to this slope over this region of delta t. So how does this algorithm look? What we get is for the x, this is in fact, as we said, there's no change in the velocity in the x direction. So as we showed here, this x velocity is just the velocity is constant. So in fact, there's actually no change in the velocity. So we don't actually have to worry about what's going on with x. Euler integration actually works exactly, but for y, because we have this g times t part, then this is actually quadratic in time, and so that's why the Euler integration is so so terrible. But it turns out that the midpoint integration solves this exactly. So just like the Euler integration solves something that is independent of time here in v, or just proportional in time here in x. Oh, I should have a t here. Well, that's a typo that I missed. What we get is that the midpoint will give us exactly the answer because this goes as t squared. So just as the Euler integration gives us the exact answer for something that goes as t, then midpoint integration gives us the exact answer for something that goes as t squared. So that's easy enough, but of course not all problems go as just some simple polynomial of time. But in this case, it works well because all we're looking at is a parabolic trajectory. So again, for y, we need to clear this array, and then we have this for loop that goes from 0 to nt minus 1. And now what we have is this dt, this delta t times this initial velocity in y minus the gravitational acceleration times tp, which is t is this midpoint. And so we have TP is defined as this midpoint time as t plus delta t divided by 2. And so that's what we're going to be putting in here as our array for time plus y naught, which is our old time step, or our old position step in y. So that's how the midpoint integration works. And so let's see what that looks like in Spider. So we have our number of steps, so we have something like 100 steps. We again go from 0 to 5 with these numbers of steps, and we define our dt as, of course, this difference in time between two of these time steps. And so again, we have the exact same for loop for x, but here for midpoint, we've substituted that g times t as g of tp. And so now if we run this, we see what pops up is this black curve is the analytic solution, where this green curve is our numeric solution. You can see that they agree very, very well, but in fact we can actually decrease this to a lot smaller number, and you can see that although it looks like it's below, if you zoom in on these points, it actually aligns very well right at these points where we're calculating it. And it turns out the midpoint routine, as I said, is exact for this case. So that's how the midpoint routine works. It's very simple. It's much more accurate than the Euler integration. It goes as dt squared, so you can have a lot fewer points to have the same accuracy as you would with Euler integration. And it doesn't really take too many more calculations. It's really simple to implement, and as I said, it's really good for something that might go parabolic with time, or some other variable. But the next one, for the next video, we'll be discussing Runge-Kutta, and that will be because we'll be discussing more complex forces, or more complex, not polynomial factors in our expressions.